Originally intended to be presented at the N-Bumps meeting on March the 25th, 2020, which was, as they say, overtaken by events. In these anxious times, I should probably start with a couple of reassurances. First reassurance, 52 is a rather large number of slides. Don't worry, it's not going to take as long getting through them as you might fear. The information density per slide is pretty low in most cases. The second reassurance is that the title of the talk is about the 3D Plaquette Ising Model, and I'm going to take a fairly leisurely route getting to that. Again, be reassured, we'll get there in the end. In fact, it's going to take me so long getting there that I thought I'd start with a trailer of what I'm going to be talking about when I eventually get to talk about what I'm going to be talking about. So the subject is this Ising model. It has classical spins, they're Z2 spins, plus and minus 1 spins, which live on the vertices of a 3D cubic lattice. And the Hamiltonian, the object that gives the energy of the model, is given by the product of 4 of the spins around the edges on this cubic lattice, the plaquettes on the cubic lattice. And it's worth emphasizing at this early point that this isn't 3D Z2 lattice gauge theory, the model that's dual to the 3D Ising model. That has got spins on the edges of the lattice, and it's also, as its name suggests, a gauge theory. This model, the 3D Plaquette Ising model, where the spins live at the vertices of the lattice, isn't a gauge theory, but it does possess some other interesting symmetries, as we'll discuss later in the seminar. The game with any of these classical spin models is to see if they have any interesting phase transitions whenever you vary external parameters like the temperature. So the objective is to calculate, or more likely evaluate numerically, the partition function, this beast down here at the bottom of the slide. The Hamiltonian appears in a Boltzmann factor. Beta here is the inverse of the temperature up to a Boltzmann constant, and we evaluate this over all possible spin configurations. And there are numerous clever numerical ways of doing this for these spin models. In very few cases, it's possible to calculate this partition function analytically. For instance, the Onsager solution of the 2D Ising model, or Ising solution itself in one dimension. So, what am I going to talk about before I get around to talking about what I'm talking about? I'll mention, or at least I'll discuss, phase transitions in general, and in spin models on a computer in particular. And then I'll move on to talk about surface models, again on a computer, because that's how I first ran across this 3D Plaquette Ising model as the dual of a particular sort of surface model. And then a shift in subject. We'll finish by having a look at quantum spin models, starting in 2 dimensions with the Toric Code, and discuss the 2D quasi-particles that exist in this anyons. And then we'll move on to have a look at 3D equivalents, models that have got quantum spin Hamiltonians in 3 dimensions and also display 3D quasi-particles, in this case with restricted mobility. And the name for these quasi-particles with restricted mobilities is fractons. So first up, phase transitions in general. The classification for phase transitions, classical phase transitions, can be split roughly in 2. We talk about first-order phase transitions whenever we have a phase transition which involves a latent heat. So there's some sort of a discontinuity at the transition point. And there's also phase coexistence. The ordered and the disordered phase coexist together. The other big class of transition is a second-order phase transition, which are also called continuous phase transitions. And these are usually characterized by something that diverges. The basic thing that's diverging is a correlation length in the model, but this drives other divergences, for instance in susceptibilities or specific heats. And you find that there's a power law decay of the correlations at criticality. Examples in real life of these sorts of transitions, well, a first-order transition, the archetypal one, is melting. There's a latent heat involved in this. It's a discontinuous transition. And the archetypal continuous, or second-order transition, is the Curie transition for a ferromagnet. If you take a ferromagnet and you heat it up, and there isn't an applied magnetic field, at some point the magnetization vanishes. You can only recover a magnetized sample if you apply an external magnetic field. And this Curie point is different for different substances, but the nature of the transition is similar for all ferromagnetic substances. What about modelling transitions like this on a computer? The simplest way that you could think of modelling a ferromagnetic phase transition by using a discretized model is to take simply plus and minus 1 spins, which is the essence of the Ising model, and place them on some sort of a lattice. The simplest interaction that you could have between these spins is to have nearest neighbour interactions. So the spins only see their nearest neighbour along an edge of the lattice. And you arrange it so that the spins prefer to be lined up at lower temperatures as the consequence of some energetic interaction, and they care less at higher temperatures. And a Hamiltonian that'll do this for you is this Ising Hamiltonian. These interactions here are along nearest neighbours in the lattice. For instance, in 3 dimensions on a cubic lattice, you'd have all of these nearest neighbours around the central red spin here. And this is called the Ising model, of course, because it was invented by Lenz and given to his PhD student Ising. The intention was to find some solvable version of the model, some given lattice, where they could see a phase transition. But that's not what Ising found. In the one-dimensional case, there isn't a phase transition. The dimension is too low to get a transition between an ordered, a magnetic phase, and a disordered, a non-magnetic phase. But this does happen in 2 dimensions for this Hamiltonian on a square lattice, and that was evaluated exactly some years after Ising's work in a tour de force by Onsager. You can generalize the sorts of spins that you have. One simple possibility is, instead of taking 2 spins, a plus and a minus, to take Q different flavours or colours of spin, and to take a Hamiltonian that looks like this. So in this Hamiltonian, this is a Kronecker delta here, the spins prefer to line up with another spin of the same colour, otherwise they don't care. And this model is called the Potts model, so called because it was invented by Dom and given to his PhD student Potts, who did some of the original work on it. And the game, both for the Ising model and the Potts model, and our 3D Plaquette Ising model, is to evaluate a partition function and then to see how this partition function behaves as we vary an external parameter, such as the temperature here. The derivatives of the free energy, which is the logarithm of this partition function, give the things that we would observe in a simulation or in real life. Energy, magnetization, perhaps polarization in different sorts of models. So, what do these observables, these things that we measure in a simulation, look like? The thing that we're most concerned in finding or measuring in a simulation is the order parameter in the model. This is something that will be 0 in a disordered phase and then 1 in an ordered phase. In the case of the Q-states Potts model, an order parameter is this magnetization given by this. So we pick out the state that has the most spins sitting in it. That's this thing here. And this M will be 1 in an ordered phase, where all of the spins are in this state, and in a disordered phase, where they're mixed round the Q different states, it won't. And we'll denote per site quantities by small letters, and total quantities over the whole lattice by these capital letters. For instance, the precise energy is given by the total energy divided by the number of spins, the number of sites on a lattice, and the precise magnetization is given by the total magnetization, this thing, divided by the number of spins. An energy can be defined as the expectation value of this thing per site, and a variance in the energy will be the specific heat. Similarly, the magnetization, we take a modulus to make sure we don't get spurious cancellations, would be given by working out the magnetization from this, and the susceptibility is simply the variance in this magnetization. These are the sorts of quantities that we'd be measuring in a simulation of a spin model, whether it was an Ising model or a Potts model or something more complicated. What do we see when we do this? Well, if we've got a first order phase transition, we might measure, it says polarization here, but I could as well have written magnetization. We'd see the magnetization would gradually decrease as we increase the temperature, but it wouldn't decrease continuously to zero. At some critical point, it would jump down to zero. So the first order transition has a discontinuity in the order parameter, as well as things like the energy, the latent heat. In the case of a continuous or second order transition, if I measured the order parameter, it would continuously go to zero and disappear at the critical point. The second order transition, the red one on the left-hand side here, would display characteristic divergences in these quantities like the specific heat and the susceptibility. The variances of the energy, the specific heat, or the magnetization, the susceptibility. So, if we've got a second order phase transition and we want to characterize it, we want to find out what the nature is of these divergences at the phase transition point. To start with, we can define a small t variable, this variable here, that's giving us in effect our distance from the critical temperature where the phase transition takes place, or I could just as well write it in terms of the inverse temperature, beta, up to, again, a Boltzmann factor. Then what one finds in general for all continuous transitions is firstly that the correlation length psi here diverges in a characteristic manner. There's an exponent, a number associated with this divergence. Similarly, the magnetization vanishes in a characteristic manner. Again, there's an exponent, a critical exponent, shown in yellow here, beta, which characterizes this vanishing. On the other hand, the variances of the quantities like the energy, the specific heat, diverge at the critical point, at the phase transition point. And again, these are characterized by particular numbers, by particular critical exponents. In the case of the specific heat, the exponent's called alpha, and in the case of the susceptibility, the variance of the magnetization, it's called gamma. And from scaling relations and assumptions about the homogeneity of the free energy, it's possible to show that there are various relations between these different exponents, and in the end, there are only two independent critical exponents. In effect, one's telling you about the energetic behaviour of the model, and the other one's telling you about the magnetic behaviour of the model. If you're doing a computer simulation, you don't have the luxury of an infinite size system in order to find out what these divergences look like. In fact, you don't have divergences at all. You'll get peaks in things like the specific heat or the susceptibility, but they won't be infinite peaks because you've got a finite size system. Computers aren't very good at doing infinity. So it's very useful to rephrase these critical exponents that are talking about a distance from the phase transition point, the infinite volume, if you like, phase transition point, in terms of slightly different quantities in terms of the linear size of a system. So if you've got a computer simulation, you'll be thinking of it as existing inside some cube, L times L times L cube, with the lattice sitting inside that cube. The correlation length in such a computer simulation can't grow to infinity. The biggest it can get is the size of the lattice L. So that means that the effective correlation length in a system, the effective maximum correlation length in a system of linear size L is just L. So I can turn around these relations that give the critical exponents in terms of t and use this to rewrite all of these divergences and vanishing relations, giving the critical exponents, to relations in terms of the linear size of the system. So we can see that the magnetization vanishes with this exponent, that the specific heat increases with this exponent, alpha divided by nu, and that the susceptibility also diverges with this exponent, gamma divided by nu. Also, in order to find out what the alpha, the beta, and the gamma are, we need to be able to find out the nu in the first instance, the exponent that characterizes the divergence of the correlation length. And one way of doing this is to notice that whenever the correlation length is of the order of the size of the lattice, we can't tell the difference between the beta that we've got, that we think is the critical point, and the real infinite volume beta, which I'll call beta infinity here. So we can make use of this relation here at the top and replace the beta c with beta c infinity and this beta here with our estimate of the critical temperature, and then turning the relation around to make it a relation for our estimate of the critical temperature, we can see that our estimate, which would be given by the peak in, say, the specific heat or the susceptibility, is given by this. So the beta infinity of C is the real critical temperature. That's what we're trying to find. Beta C of L is the best that we can do on a lattice of size L. And our estimate will shift with the size of the lattice that we're simulating. So the trick with finite size scaling is to simulate differently sized lattices and then use that information to extract, first of all, nu, and then once we have an estimate for that, the other critical exponents from measurements of M, the magnetization, C, the specific heat, and chi, the magnetic susceptibility. So to summarize, if we've got a computer simulation where there's a second order phase transition in the model, we don't see divergences, we can't have infinities on our finitely sized simulation. What we see are peaks in the specific heat that grew as L to the alpha over nu for a system of linear size L, and L to the gamma over nu in the susceptibility. And we also see that our transition point estimates shift like this. And these numbers, these critical exponents, vary with the sorts of models that we have. So the interest in simulating a model with a potential second order phase transition is in finding what these critical exponents are. There's a finite set of universality classes for these phase transitions. Different looking models can fall into the same universality class. The game is to determine what this universality class is, to extract the critical exponents from finite size simulations. What about first order phase transitions? So these are perhaps more prevalent in nature, but when it comes to numerical simulations, they've tended to be the poor cousin. And the reason for that really is that you might think there's only one sort of first order phase transition. There's lots of different potential critical exponents to find, lots of different universality classes to find in the case of a continuous phase transition. Not so for a first-order phase transition. Nonetheless, there's still a sort of almost trivial finite size scaling, which we can extract from the following considerations. If you have a look at a time series of some quantity at a first-order phase transition or near a first-order phase transition in a simulation, what you see is phase coexistence. So the model flips between being largely in the ordered phase to being largely in the disordered phase. For instance, in this graph on this slide, you can see that there's a sort of bistability. It's being simulated right at a phase transition point. So it's a Potts model where there's a first order phase transition sitting more or less at its phase transition point. And if you plot a histogram of the energies, you get this characteristic double peak structure. So there's both a low energy phase and a high energy phase present. And we can use this observation to extract the scaling that we would expect in a simulation. So suppose we had a fraction, let's call it WO for ordered, in the Q ordered phases. So I'll assume I've got a Q state Potts model where there are Q potential ordered phases. And the energy of this is EO for the ordered energy. That means there'll be a fraction 1 minus WO in the disordered phase with some other energy, ED, for disordered energy. So the energy moments trivially become this. I simply weight the ordered and the disordered values by the appropriate fractions. And if I've got the energy moments, I can calculate things like the specific heat. So the little e's here, remember, are per site quantities. I calculate a per site variance in the energy, which gives me the specific heat. There's a factor of beta squared by definition in front of it. And then to get the total specific heat, I need to include the volume of the lattice, L to the D. So the maximum of this specific heat function in this simple approximation to a first order phase transition will be the maximum of this fraction, W0 times 1 minus W0, which obviously occurs whenever W0 equals WD equals a half. So that means that the maximum of the specific heat is given by this value. The delta E is the difference between the disordered and the ordered energy. The beta is the infinite lattice value of the transition temperature. And the scaling simply goes with the volume. So there are no critical exponents like alpha or gamma sitting here. There's simply a volume scaling for this first order phase transition. And we can extend the argument slightly to see how our estimates of the critical temperature itself change with the size of the system. So if we make the free energy of the ordered phase FO, the free energy of the disordered phase FD, then the fraction of the system that's in the ordered phase will be given by these Boltzmann weights, and they're Q ordered phases, so I've got to multiply this by Q. But there's only one disordered phase, so I get a simple Boltzmann factor here for WD. So we divide these, we take logs, and we expand around the infinite volume critical temperature, beta infinity. And when we do that, the constant terms in the free energy match up. The next term in the Taylor series are the energies, so subtracting these gives the difference in the energies. And then we notice that at the peak, W0, W ordered rather, is equal to W disordered, so the logarithm is 0. And just as we did for the second order phase transition, we can turn the expression around to make it into an estimate for the finite size critical peak in the specific heat. So beta infinity is, if you like, the real infinite volume value of the critical temperature. Our estimate coming from the peak in the specific heat, where WO is equal to WD, is given by this. And the shift isn't something to do with L to the 1 over nu now. It's simply a volume shift again. So we can summarize the behavior of numerical investigations of first-order phase transitions by saying that peaks in quantities grow as L to the d, or if you prefer, the volume, and the transition point estimates shift as 1 over the volume, or 1 over L to the d. And this should be true for all first-order phase transitions that we choose to simulate. Unlike second-order continuous phase transitions, there aren't different critical exponents to find. There's volume growth of peaks and a 1 over volume shift of our estimate for where we see the critical transition. So that's enough about phase transitions both in general and on computers. I'm gradually edging towards talking about the 3D Plaquette Ising model itself. And I first ran across it, and indeed it was first formulated in the context of surface models on lattices rather than spin models. So let me discuss these. There are various ways that you might think of simulating a surface that's made up of square plaquettes that are embedded in a cubic three-dimensional lattice. You could do the obvious. You could have the plaquettes themselves and assign some weights to different configurations of the plaquettes and go away and simulate that directly. An alternative way of doing such a simulation would be to consider that the surfaces that you're interested in, you have some gas of surfaces in your lattice, you should consider that the surfaces that you're interested in are the spin cluster boundaries of some spin model. So where a spin changes, spins on an edge change from plus to minus, you consider that there's a plaquette of the surface. So either I could assign edge spins to the surface. If they're plus, there's no plaquette. If they're minus, there's the plaquette dual to that edge. Or I could look at the vertices at the end of the edge and split them up as these Ising spins, sigma I and sigma j. When these multiply, when the product of them is minus 1, I consider that there's a plaquette between them. And if I want to count different sorts of surface configurations, for instance, if I want to weight the areas of the surfaces that I've got on my lattice, but maybe also the intersections and possibly the number of edges on these surfaces, I can do this by considering the surfaces to be the duals of an extended Ising model. So I allow interactions between nearest neighbour spins along edges, but I also allow interactions between next to nearest neighbours and plaquette interactions. So this is the first appearance of a 4-spin plaquette interaction in the story. And this was first considered some years ago by an Italian group, R.K.P.C, Colangelo, Gonella and Maritan, and they showed explicitly that a Hamiltonian for surfaces composed of plaquettes on a cubic lattice, where we weighted the area, the total area of all the plaquettes, the total number of edges, and the total number of intersections, was in 1-to-1 correspondence with an extended Ising model, which is shown at the bottom here. So the Ising model had 3 couplings. There were nearest neighbour interactions with a coupling J1, next to nearest neighbour interactions with a coupling J2, and, here's our plaquette interaction again, an interaction between 4 spins round the face, round a plaquette on the lattice. And the couplings for the Ising model, J1, J2 and J3, could be related to the couplings for the surface model here. And we simply do that by having a look at the individual configurations that we could get back here. If we count up all the different possibilities, it's possible to show that this spin model is in one-to-one correspondence with this surface Hamiltonian. In general, the area term will dominate. So the phase behaviour of your surface model will look like the phase behaviour of the three-dimensional Ising model, which has got a continuous phase transition. But it's possible to tune out the influence of the area of the plaquettes. If we go back and we have a look, we can see that the area term depends on both the nearest neighbour and the next to nearest neighbour term. And if we choose different signs and the appropriate difference in weights, factor of 4 to 1, we can get these to cancel. So this Hamiltonian, which was first investigated by Savvidy and Wegner, who also invented lattice gauge theory, by the way, can be written out like this. So the next to nearest neighbour and the nearest neighbour term have differing signs and a factor of 4 difference in their couplings. So there's a free parameter in this model, kappa, which also will appear in the coupling of the Plaquette term as well. So if there's no area term, this Hamiltonian is the one that you want. And now we notice one particular example in this family of Hamiltonians. Whenever kappa is equal to 0, only the Plaquette term is left. And the kappa term, if we trace it back to the surface model, is the term that weights the self-intersections of surfaces. So if I've got a surface model where I weight only the edges of the surfaces that are embedded in a cubic lattice, I can represent that by this Plaquette spin Hamiltonian. And that was how it was originally discovered, or how it originally became of interest, as a potential model for random surfaces on a cubic lattice. So now we've finally arrived at our 3D Plaquette Ising model. It's related to Plaquette surfaces on a cubic lattice. It's also, in itself, an interesting spin model to investigate. So the question is, does it have any phase transitions? If so, what order are they? And also, what are the order parameters for these phase transitions? Is there standard magnetic order, for instance, or is it something different? And I want to embed a little morality story about disbelieving PhD students in this part of the story as well. So, we've finally arrived at the subject of the talk halfway through. We've got a lattice Hamiltonian, a spin model with plus and minus 1 spins, which live on the vertices of a Q3D, three-dimensional cubic lattice. We've remarked at the start, many hours ago, that this isn't three-dimensional Z2 lattice gauge theory, where the spins live on the edges. What we want to do with this model is investigate it, see if there are any interesting phase transitions, and see what the behaviour of the model is. And before I do that, I should make one more aside. Duality for spin models. So duality for lattices, geometric duality, is a well understood concept. If you've got a square lattice, it's self-dual. If I've got a triangular lattice, its dual is a hexagonal lattice, and vice versa. So you get the dual by putting a vertex in the middle of one of the faces, in the case of a two-dimensional lattice, and joining them up and seeing what you get. And of course you can generalise this to higher dimensional lattices as well. There's also a duality for the spin models that live on the lattice and its dual lattice. This is Kramers-Vanier duality for spin models. And this swaps not just the two lattices, it swaps the high temperature and the low temperature phases of the model. So the dual model's high temperature phase is the low temperature phase of the original model. And you can show that the coupling constants in the two models, the original and its dual, are related like this. For instance, a square lattice Ising model, if you have a look at a low temperature expansion, you get something that looks like this. If you go to the dual, which again is a square lattice, and have a look at the high temperature expansion, you get this, similar in form, so long as you make this identification between the different parameters. For the Plaquette Ising model, if you carry out this duality operation, what you find, somewhat surprisingly to me at any rate, is that the dual of this Plaquette action for the three-dimensional lattice is this, where we've got nearest neighbour interactions between two different sorts of spins. Fancy name for this is an anisotropic Ashkin-Teller model. So there's one set of spins that are coupled along one direction, the x direction. There's a different set of spins that are coupled along, say, the y direction, and then along the third direction, there's an energy coupling between both sorts of spins. So the high temperature phase of this model looks like the low temperature phase of this one, the dual model, and vice versa. Now the stage is set for the morality tale. Here's an excellent exercise for a starting PhD student. Simulate the 3D Plaquette Ising model, this thing back here, the Plaquette action, and its dual. Do a careful job of determining the transition point of both of them, and obtain consistent estimates of this transition point. So for a starting PhD student, there's a relatively simple, well-defined model, and it was known from previous work that the Plaquette Ising model had quite a strong first-order phase transition. So it's one of these apparently rather boring numerical models to simulate. There's only one sort of first-order phase transition, so there's no difficult to find critical exponents. Things that have peaks should grow like the volume. The phase transition points estimates should shift as 1 over the volume. So in 3 dimensions, things should grow as L cubed and shift as 1 over L cubed. You should be able to find, in addition, a consistent value for the phase transition point by simulating the model and its dual model, and then using the relation between the couplings and the dual couplings to match up the transition points. You give it to your PhD student, who happened to be Marco Mueller in Leipzig, who was in Professor Wolfhard Janke's group there, a collaborator. You tell him to go away and do exactly this. So he determines the critical point on variously sized lattices with periodic boundary conditions, and he does the fits that you would expect. So the estimate of the critical point should shift as 1 over L cubed, 1 over the volume, and peaks in things like specific heats should grow with the volume. What he found from his simulations was that the original model, the Plaquette model, had this estimate for the phase transition point. The dual model, the one on the dual cubic lattice, had this estimate for the phase transition point. There are clever ways of doing the simulations, so the error estimates are reliable. And if you translate the dual one back to the original one, if anyone's paying attention, there's a factor of 2 difference between the definitions that I use here and the ones that I gave earlier. This is because there's a factor of 2 difference in the definitions used for beta in the simulations. What you find is that the estimate from the dual model for the critical point, the transition point, is given by this. And if you compare it with the estimate from the original Plaquette model, these estimates are about 30 sigma apart. They don't look very much, but with these error bars, they're 30 sigma apart. So that's either a discovery or a screw-up. It's a PhD student. He's just starting out in the business, so it's clearly a screw-up. What do? You ask the student to go away and check his erroneous results. He's quite a good student, so he repeats the simulations with a completely different code base. I think the original ones were C++. For fun, he decides to do it in Fortran. Some people have got a very strange idea of fun. And he comes back with exactly the same results. So you go away and you ask the student to repeat the simulations again, or you stop and you think, which is probably what you should have done first before telling the student to repeat things. And what you think is there anything special about the Plaquette model and its dual, compared with, say, Potts models, which have first-order phase transitions, but where there's no strange scaling effects whenever you compare the model and its dual? Well, there is. The Plaquette Ising model might not have gauge symmetry like 3D lattice gauge theory, but it has a subsystem symmetry. If you look at a single cube, you can see that you can flip one of the plaquettes on that cube without changing the energy. And you can do this in any of the directions, X, Y, or Z direction, and then you could do this for any set of cubes in the lattice. So you can flip an entire plane of spins running through the lattice in any direction, even when these planes of spins interact with each other. And that doesn't change the energy of the system. So what that means is that the ground state of the Plaquette Ising model is exponentially degenerate. On a system of size L cubed, there will be 2 to the 3L possible ground states. You can flip any of the L planes of spins in the 3 directions from a state where all of the spins are, say, in the plus direction, and that'll still be a ground state of the system. Wegner and a student of his, R.K.P.C, did some low temperature expansions for the Plaquette model, and they observed that this was still the case throughout the low temperature phase. So you could flip these planes of spins even at finite temperature, and this didn't affect the fact that it was the lowest energy configuration. So what you have is a system with an exponentially degenerate number of low temperature phases, ground states as well. And it's true for the dual model as well. You just have to choose which of the spins that you're flipping. There was a sigma spin and a tau spin. So I'll put, say, the sigma spin first in these pictures and the tau spin second. But I can still flip any one of these planes of spins on a cube without changing the energy. And I can still do this throughout a cubic lattice. So, both the model and its dual have an exponentially degenerate number of low temperature phases. So a typical ground state, either in the model or its dual, looks like this. And this persists, as we've noted, into the low temperature phase as well. So it's not all either plus or all either minus in the low temperature phase or in the ground state. It's some peculiar mixture like this, obtained by flipping planes of spins throughout the lattice. So let's ask what happens to our expected finite size scaling in a first order phase transition when we've got exponential degeneracy. We can go back to the relation that we had before and notice that the number of low temperature phases Q appears in our finite size scaling relation for the shift in our estimate of the critical temperature. And if we simply plug in the value that we have for Q, so it's 2 to the 3L, or e to the 3ln2 to the L, the expression that we have for any first order phase transition becomes the one that's given second here. So instead of shifting by L to the D, our estimate of the critical temperature, the phase transition temperature, shifts as L to the D minus 1. So in a three-dimensional lattice, that's L squared. Now we go back and we try and compare our estimates of the critical temperature with a different shift. So in these pictures, the original model is on the left-hand side. The dual model is on the right-hand side. The fitting range, minimum and maximum values of L, are given on the axes, and the quality of the fits are shown by the pixels. So orange or red, however it comes out on your screen, is bad. Green is good. And we can see that the range of fits is best whenever we take this modified L squared scaling. So what the student had actually discovered was that the exponential degeneracy of the ground state and low temperature phase for the Plaquette Ising model changed the scaling at the first order phase transition. So don't always ignore PhD students' numerical results. This unusual numerical result was the consequence of a subsystem symmetry. So it's neither a global symmetry nor a gauge symmetry in this Plaquette Ising model. The subsystem symmetry changed the finite size scaling at the first order phase transition point. And now for something completely different, but still related. So I'm going to switch to talking about quantum spin models. So instead of simply plus and minus 1 sigmas, our sigmas are now Pauli matrices, and the states living on our lattice will be qubits. So we'll have zeros and ones, bras and kets, living either on the edges or on the vertices of our lattice. And the model I'm going to start talking about, apparently completely disconnected from Plaquette Ising models that we've been talking about so far, is the Toric Code. But again, bear with me. We'll wind our way back to the Plaquette Ising model eventually. Of course, the big feature of the Toric Code is that one sees two-dimensional quasi-particles in it, and these have anyonic behaviour. And we'll see in our discussion that you can think of obtaining the Toric Code by gauging a global symmetry, the standard Ising model. So the Toric Code, what is it? Two-dimensional square lattice, periodic boundary conditions, so it looks like a torus if you like, and the Hamiltonian, now a quantum Hamiltonian, so there'd be Pauli matrices, which I'll call tau here rather than sigma, and the Pauli matrices will live on the edges of a square lattice. The Hamiltonian contains two sorts of terms. A terms, where they're a product of X Pauli matrices around a vertex, so I've coloured that in blue in this picture, and there'll be B terms, where the Pauli matrices are given by the product round a plaquette on the lattice. And we take the product of the Z Pauli matrices, which I'll call tau Z here. And these two terms, the A and the B term, commute with each other. The Hamiltonian's given by this. Two couplings, a star term and a plaquette term. Quantum Hamiltonian. The ground state for this model is a sort of loop soup. And I can think of it either in a picture that favours the plaquette, and the plaquettes are magnetic terms, or in a picture that favours the crosses, the vertices, the blue terms, and these are electric terms. The ground state, or a ground state of the model, is given by this loop soup. So if I take the plaquette as my favoured term in the Hamiltonian, these zero terms will be the ground states of the plaquette terms. But I also have a vertex term, the blue term, coming from the tau x variables here. So I've got to project out all of the configurations which don't minimize the vertex terms, and I do that with these factors in front of all of the zeros. So the ground state be a product over all possible factors like this, taking account of the vertex terms, acting on these edge qubits, which are already in the ground state for the B terms. So this is a sort of loop soup, and it's a loop soup of closed loops. Defects appear in this ground state configuration as the ends of strings of either the Z Pauli matrices, the magnetic ones if you like, and the X Pauli matrices. So the electric defects are at the end, perhaps slightly counterintuitively, of the Z Pauli matrices, and the magnetic defects, are at the end of strings of the X Pauli matrices. And if you braid these excitations with the defects on the ends of lines of the different Pauli matrices around each other, you see that they've got an ionic behaviour with respect to each other. So if we call the electric excitation E and the magnetic excitation M, the E and the M are bosonic with respect to themselves, but if I take an E for a walk around an M, it gives a -1 phase, so they're anionic. And of course there are other interesting properties of these models. In particular, the one that originally excited interest in them, the topological degeneracy of the ground state, because I could wind a string of these excitation operators all the way around a torus. And since there are 2 ways that I can do this, I find that there are 4 ground states on a torus for the toric code. So it's got a topological behaviour. The toric code Hamiltonian looks as if it was just pulled out of thin air to obtain these interesting anionic properties. But it's actually lurking inside a simple Ising model in 2 dimensions, a quantum Ising model. So if I start with a quantum transverse Ising model, whose Hamiltonian is given by this. So I've got the nearest neighbour term, but now the external field term to flip the spins would be given by a different sort of Pauli matrix. So if the nearest neighbour interactions are between the Z Pauli matrices, and I've called them sigma Z here, for reasons which we'll see in a second, the flip operator, the one that flips the spins, will be given by sigma X. This is the standard Ising model. It's got a global symmetry, so I can't flip single spins and leave things unaffected. But I can gauge the model. I can insert spins in the edges between the sigma spins. Let's call these tau Z. And I can give these dynamics by inserting a Plaquette term for the tau Z spins. And now, if I have a look at the beta to 0 limit of this gauged transverse Ising model, in other words, the high temperature limit, and demand gauge invariance, first of all, gauge invariance will give me this. So if I flip a sigma spin, I have to flip all of the tau spins on the edges attached to it. If I do this, I've got a gauge invariant state. So if beta goes to 0, the first term vanishes. I can replace the sigma x by the product of the tau x's for gauge invariant states, this term here, and I leave the Plaquette term. So we've arrived at Kitaev's, the original gentleman who formulated the toric code. It's the high temperature phase of the transverse Ising model, the quantum Ising model. I simply have to gauge an Ising model with a global symmetry, look at its high temperature phase, and I recover the toric code. So what? Let's do something similar in 3 dimensions. And we'll consider a model which has quasi-particle excitations in 3 dimensions with restricted mobility. And these restricted mobility quasi-particles in 3 dimensions have been dubbed fractons. In particular, the fractons are quasi-particles with restricted mobility that don't move at all. If you've got a quasi-particle that can move along a line, it's a lineon. I didn't make these names up, so my apologies. If you have a quasi-particle that can only move along a plane in 3 dimensions, it's a planion. And we'll see that we can arrive at this x-cubed model with these interesting, for some, fractonic excitations, not by gauging a global symmetry, but by gauging a local symmetry, or rather a subsystem symmetry. Exactly the sort of symmetry that we have in the Plaquette Ising model. So the x-cubed model, it's one way one might think of generalizing the Toric code to 3 dimensions. It's not the 3D Toric code, that's another way of generalizing the Toric code to 3 dimensions. Instead of taking products of spins around a plaquette, you take products of spins around a cube. And instead of taking a cross operator in 2 dimensions, you take 3 possible cross operators around a vertex in 3 dimensions. So one of these is in, say, the XY plane, one of them is in the YZ plane, and the other one is in the remaining plane. So the B's are the cross operators in the different planes. The A is the cube operator. And the resulting quantum Hamiltonian is given here. Instead of having quasi-particle excitations which can move any old way, which was the case for the Toric code, it turns out that the excitations in the x-cubed model have got restricted mobility. So first up, the electric excitations. These are given by membrane excitations of the Z polymatrices. So if I take a chunk of these Z's in a configuration like this, the electric excitations can only exist at the corners of this membrane, and they can't move anywhere. I've got to increase the size of the membrane to move these excitations outwards. It costs me energy to do that. The magnetic excitations follow from strings or live on the strings of the X polymatrices. But because of the way that these interact with the cross terms, the star terms in the Hamiltonian, they can only move in lines without creating additional excitations. So if I want to turn a corner, I have to create another excitation. So straight line motion costs nothing for these linear excitations. So if I look at the cross terms which are excited, apologies for the rather sketchy drawing here, I can see that if I move along in this direction, a Z and an X cross are excited. But if I turn a 90-degree bend, a Y and a Z cross are now excited. And to get from here to here, I've got to excite an XY cross as well. So all 3 of these could meet up and annihilate. But if I want to turn a corner, I've got to generate a 3rd one as well. How do we arrive at this x-cubed model? So you could simply pull it out of thin air like you did with the Toric code, or you could try following a rather simpler procedure to creating the Toric code from an Ising model. In this case, we don't take the standard Ising model, we take our Plaquette Ising model. So we take a 3D Plaquette Ising model with quantum spins in an external field. So the flip operator is now the polymatrix X, and we gauge the subsystem symmetry rather than the global symmetry. And we can do that by putting a tau spin at the centre of each plaquette. the centre of each face. So I've indicated that as a tau square of z here. And we follow a similar route to creating the toric code out of the Ising model. Having gauged the symmetry, we introduce the equivalent of the Plaquette flux term in the two-dimensional toric code. In this case, it's a sort of matchbox flux term, not a full cube. And this gives the cross terms which appear in the x-cubed model. So, the gauged subsystem symmetry results in this Hamiltonian. There's the original Plaquette terms, there's the gauge spin tau z, and there's these cross terms, which are the dynamical terms for the tau z. Again, if we look at the high temperature phase, and if we impose gauge invariance, what we recover, what we end up with, is the x-cubed model. So, to summarise, the Plaquette Ising model has a subsystem symmetry. That's its unique selling point. This affects the finite size scaling at first order phase transition, which is what it displays, because it's got an exponentially degenerate number of low temperature phases, an unusual feature. If we switch our focus to quantum Hamiltonians, we see that if we gauge this subsystem symmetry, we get fractons, reduced mobility anyons. Not surprising, maybe. So the original model has got a sort of reduced mobility symmetry. It's not the full symmetry, it's not global, it's not a local symmetry. Certain subsystems can flip. There's symmetry there. So this gets picked up whenever the model is gauged and inherited by the fractonic excitations. Some of them are confined, they can't go anywhere. Other ones can only go along lines. There are related continuum theories, foliated field theories, and symmetric tensor theories that are related with these fractonic models. It's been an area of considerable interest in condensed matter theory over the past couple of years. There's been an explosion of work on it. These foliated field theories, for instance, look like this. So if I've got a cubic lattice, I can think of slicing it up in different ways. And the field theory is composed of a three-dimensional toric code, which can be written like this, and a set of two-dimensional toric codes which are embedded inside it. The fractonic theories have also been related to symmetric tensor theories, and the archetypal symmetric tensor theory, apart from gravity, is elasticity. And it's been shown that there's the explicit duality between two-dimensional elasticity and fractonic theories in two dimensions, a sort of U1 continuum version of the fracton theory in two dimensions. The people involved in this are shown at the bottom here. And this also shows that the apparently exotic feature of limited mobility for the excitations appears in other places as well. In elasticity, disclinations, in effect, are fractonic excitations. They're pinned in place, they can't move, whereas dislocations can only move in particular directions, just like the excitations in the x-cubed model. The theories, the continuum theories associated with this class of models are typically, as we've noted, symmetric tensor gauge theories. So they're not anti-symmetric tensors, as in higher form gauge theories, but symmetric tensors. Enough, the end. References. The original 3D Plaquette Ising model, which was called the Gonihedric model, for reasons connected to the surface theories, was formulated by Savvidy and Wegner. The numerical stuff that I talked about can be found in these references, and you'll notice the student got his revenge. The first author on all of these papers is the student. The last author is the disbeliever. Fractons. If you want to read about them, there's been an amazing amount of work recently. Google fracton One guy who's been particularly active in the field is Michael Pretko. There's quite a few good videos of seminars by Fracton practitioners as well. The name's a misnomer. It was used for something else previously. So Fracton was previously used to describe excitations on fractal lattices, phonon-like excitations on fractal lattices. This is something different. So you want to be having a look at more recent, greater than or equal to 2016 hits on Fractons, if you want to read about them. Okay, that's us, I think. Enough is enough.